So my name is Corné. I'm an audio software developer from the Netherlands. And I want to talk about an audio live coding environment that I've been designing for the past year or so, or been developing. I'm going to present mostly from my editor because it's more interactive that way. So I'm going to start with a little demo, audio demo. So that's abrupt ending, but what you've been hearing is sound that is generated in real time by this code that you see on the screen, basically. So I want to talk a little bit about the inspiration for this system, the design goals that I had when building it. Go over some of its features. It's still in active development, but there's some stuff to show. Talk a little bit about the implementation details, and if I have time, address some future plans that I have. So the inspiration came from many things. I'm not the first person to get the idea to generate sound with code. There are many systems, some of which have been around for decades. For example, C-Sound, I think is from the 80s. There is Super Collider, which is a pretty well-known system that's also been around for something like 30 years. There's Max and PD. I think if you're active in the audio world, then you've probably heard of these. These are actually visual languages. So this is a screenshot from PD or Pure Data. And you can see it's kind of like a visual programming language where you connect boxes together with wires, which turns out it's quite a good way to program audio systems. I mean, it kind of works like a modular synth, right? So you have different modules and you connect them together with cables, and sound flows through them. So that's basically, a nice way to work. For me, I did want something textual, and the reason for that is that Max and PD are, they're designed to also be able to be used by people who are not primarily programmers, so artists and musicians. So in that way, they're a bit more approachable than textual programming maybe. But I built this primarily for myself, and I already learned how to program, so I want to be able to leverage those skills. And I found there's relatively little transferable knowledge between textual languages and visual languages. It's like a whole new paradigm. Well, there are a couple more tidal cycles, or in Strudel, which is a JavaScript port of tidal cycles. Tidal cycles is, I guess, a bit more high level. So I have Strudel open here somewhere. You can see I can hit play. It works in the browser actually. But here you work more on the level of individual sounds rather than like audio signals. Those are inspirations for the system basically. Most of them are far more developed because they've been worked on for decades basically. But I thought it would be a fun thing to try to implement something like this myself. It's written in Rust. I think most people probably heard of Rust, so I don't really need to go into that. And it's also built on two other technologies. One of them is Codo, which is a programming language by Ian Hobson, who is actually presenting at ADC next month as well, I think. And he's a Rust programmer, and he designed this programming language as an extension language for Rust. So the way I think about it, it's kind of like a Lua for Rust. So Lua is a language that is easily embeddable inside C and C++ applications. So if you want to make your application scriptable, where you can yeah, kind of script things at runtime without having to change your C or C++ code, then Lua is a really good choice for that. And kind of in the same way, Koto is a similar thing, but for Rust applications. And it's also, it has really minimal syntax. So it's like super quick and easy to write, and super easy to get things out of your head, like into the code. So I thought that was a really nice fit for yeah, what I was trying to do. So basically, I built like a audio engine in Rust and made it scriptable with Koto. And for the actual DSP, so like the oscillators and filters, I lean quite heavily on a library called FunDSP, which is a Rust library for audio processing and synthesis. So it has things like oscillators and filters, stuff like that. So I didn't have to write all of that from scratch, basically. Then something about the design goals. So I had a few goals in mind when designing Ohm. The idea was to be able to express musical ideas elegantly and concisely. So if you try to develop like audio algorithms or you experiment with musical ideas in C or C++, there's quite a lot of boilerplate that you have to write. And every time you make a change, you have to kind of recompile your code. So it's a bit more low level. So it would be nice to have something where you can just experiment with audio and while staying in the flow, basically. So without having to think too much about like syntax details. I wanted a terse and minimal syntax, so basically that's what Koto gives me. I wanted it to be interpreted in real time, which means there's no compile step, right? So one way to show that, let me comment this code out. So if I have like a piece of code, so here it's basically a saw wave going into a low pass filter. And if I run this code, oh wait, I forgot to save. And so I want to change the frequency of the oscillator. I can just change it and hear the results immediately. By the same way I can change like the cutoff frequency of the filter. So the idea is that you make a change and you can hear the result immediately, and you don't have to wait for anything to compile. I wanted it to be dynamically typed, which means there's no types to worry about. So in a way that's easy, because it turns out everything in the system is basically the same type, which is a signal. So just a stream of numbers. So even if I just type a 0 and I have a little print function, so I print it to the console, you can see it's like a continuous stream of zeros being generated and sent to the audio output, right? So that way everything is kind of like a stream of numbers, and you just pass these streams of numbers into different nodes. I wanted it to have an open design, so that basically means that I didn't, for example, want to have a synth that let me turn off Copilot. That have to like, I give it a pitch and a cutoff frequency for the filter or something like that, and have an entire synth in one function. I kind of want to take these things apart and just have like a separate envelope and a separate filter that I can route in different ways and kind of build the synth on the fly, right? So kind of an open design that way. And I wanted to have sensible defaults. So for example, if I just generate a saw wave and I don't specify a frequency, it chooses one for me. And if I just pass it to like a low pass filter, and I don't specify a frequency, it just picks like a sensible frequency, right? So that way you can, I don't know, you can just try things out really fast without having to fuss over all the details. So then, I wanted to go over some features that are in the language. So there are a lot of like built-in audio nodes. So there are oscillators. So don't know, like a triangle wave or a saw wave or a sine wave. Those are all built in. There are filters. So there's a low-pass filter, and basically the low-pass filter is defined here. Make it a bit more readable. So the low-pass filter is just like a convenience function that takes an input signal, a cutoff frequency, which is optional, and a resonance value. And inside the function body, I take the input and I send it into a state variable filter, which is like an audio node that's built into Rust, that is set into a low-pass node, and that get the frequency and the resonance as parameters. So there are also some different types of filters, like a Moog filter, one-pole filter for smoothing signals. So there's various stuff built in. There are envelopes. So I can take, again, a saw wave and multiply the output by an envelope, and this is an AR envelope, so attack release, super simple envelope, and I triggered this like every well, at 1.5 hertz, right? It gets triggered, and then we kind of shape the volume of the signal over time. So you can use envelopes like that. Of course, you can also use them on filters and stuff like that, so you can kind of recombine them. There's built-in effects. So here we have, for example, flanger and a delay. So you can kind of hear the effect. Sorry, I said delay, I meant reverb, of course. There's built-in sequencers. So here I have a sequencer that is sequencing an array of values. So these nodes, so C3, E3, they get kind of played in sequence by this trigger. And then I have a little utility function, which means pitch to frequency. So it converts this to frequency, and I pass that frequency again to a saw wave oscillator. So I do this. So then I can sequence different values. And again, you can use this also to sequence other things like cutoff frequencies, or you name it. You can, of course, combine these things. There's audio file playback. So I can load a file from disk. I have a little folder here with samples, and those are just like small wave files. And when I type the name of one of these, it gets loaded. So now it's just looping this file. I can play it back at different speeds. So basically the way it works is I have this file function. I load it with the name of the sample I want to load. I put that into a variable, and then I can call the play function with this variable, and that will play it back. I can do the same thing with file, or with let's say sample buffers, right? So I can define a buffer which has the length of the sample rate, which is 1 second in the current sample rate, and then I can kind of write a saw wave into that buffer, which is happening here, and then read it out, and maybe read it out at a different speed. And it turns out you can do all kinds of things with this. So, for example, here I've defined like an echo or a delay effect in terms of using a buffer, right? So I have a buffer, and I read from it, and then I filter the sample that is in the feedback loop, and then write it back into the buffer. So this way you can, kind of define a delay effect entirely in Koto. I also have a one-pole filter somewhere. So this is like a filter implemented with a buffer. So then we just need one sample to store the previous sample, but we can actually use this to implement the filter. It's not very efficient to do it this way, obviously, but I thought it was interesting that it was possible. So yeah, those are the sample buffers. Of course, there's ways to do abstraction. So, which is functions. There's no classes or anything, but there are functions. So I can define a function here. I have a function that is a hi-hat. So I pass some noise through an envelope and then through a bandpass filter. And then I get kind of a hi-hat sound, right? Well, there are like arithmetic operators. So you see them already. Here's the multiply operator, for example. And that gets kind of overloaded by these audio nodes, right? So if normally in Koto, in the language, you have, of course, a multiply operator. But if you multiply two audio nodes, they multiply their signals. So you can use that to do kind of DSP operations. Well, there's all kinds of utility functions, for example, to convert frequency to pitch. I mentioned already. There's some useful constants. So there's stuff like pitches or scales that you can. So a scale major is an array of pitches that you can use to do stuff. And one really nice feature, or that I found really nice in Koto, is the pipe operator. So normally in like a normal, I don't know, like any C-like programming language, the way you would pass functions to each other would be in this way, right? So I have a saw wave oscillator. I pass its 100 hertz as its argument, and then I pass the output of the saw as an argument to a low-pass filter. And I mean, that works. This is also valid syntax. But it's kind of difficult to read, right? You have to read it from inside out. So what you can do in Koto is, I think some other languages like Elixir also have this, but you can pipe the output of one function into the next function. So basically what this does is it takes the output of this function and applies it as the first argument to the next function. So here we apply the output of the add function to the square function, then to the multiply function. And that way you get kind of you can read it from left to right, like a signal flow. And the way I set it up here is that the first argument of a function is always the input, right? So it's an input signal. So this way I can kind of arrange nodes with these pipe operators and read them from left to right. So that's really, convenient. I think I'm running a bit short on time, so I'm going to skip some stuff. So one thing that was really important to me is hot reloading, right? So I showed already, I can make a change and I hear the result immediately. So here I have a sine oscillator and I modulate the pitch with an LFO. And one thing that I don't want is, for example, when you change the frequency of the LFO, that it kind of jumps, right? You want a smooth. So if I change the value, you never hear like a discontinuity in the sound. It always kind of it continues where it was. And the way that works under the hood is basically, so when I re-evaluate the code, I create a new audio graph. So the code gets turned into an audio graph. So for example, here we have a fixed value that's going to an LFO, and the LFO is going into a multiply operator that's multiplied by another fixed value. And some of these nodes, they have state, right? Like the LFO has phase as its internal state. So when we reevaluate the graph, we kind of copy the state from the old nodes to the new ones wherever possible, right? So that, in that way we get basically no no interruptions, no discontinuities in the sound. So that was that was quite important to me. Yeah, seems like I'm pretty much out of time, so I think I'm going to skip the rest. I just want to mention the code is open source. It's on GitHub. So I think the link to my GitHub is also on the speaker page. If you want to check it out, you can find it there. So yeah, this was my talk. Thank you for listening.